Let's resume with an example of what can go wrong if you're not careful and you would bound the time complexities differently or not at all. So suppose the decoder D, which sends inputs X to outputs C, is bound by O beta of X instead of O beta of C, or not at all. Then something we would not like happens. So let U be a universal Turing machine and let T count be a Turing machine which does the following simple thing. On input X, it just starts prepending once at every time step. It appends 1, 1 to the beginning of this sequence. So it's just a counter of time in some sense, which on input X at every step prepends a 1 and moves left. Then we have the following situation. If we start with some input C, our encoding can just be the identity map. And now what happens after our delay can be 1, a constant 1. So what happens after k steps? Here we will have C, possibly with one blank space to have some delimiter. And here we will have exactly k once. So what this Turing machine did is it preserved the input and it just tracked the time. So now with this information, we can define the decoder to simply read off that number of time steps and iterate the function fu for that amount of time steps on C. So if the time complexity of the decoder was bound by its input length, then it's pretty clear that it's fine. It would be bound by, I don't know, some polynomial or something. It's because internally this Turing machine blew up the size of its non-blank configuration such that we can then hide the computational power into the decoder. So then T count can simulate the universal Turing machine. Yeah. So what would be some reasonable properties that we would like from the local simulation? Okay, so definition, Turing machine T is locally universal if it can the Turing machine at every, it starts with C, it moves left, maybe leaves one blank space, and then it writes a 1. At every time step it does that. So after k time steps there will be exactly k ones, just to know what is the time. Yeah. If it can locally simulate every Turing machine. So what should be some reasonable properties of local simulation? So it should be transitive and reflexive. That would be quite nice. So if T1, okay, if T3 simulates T2 and T2 simulates T1, then we should have that T3 simulates T1, and we also should have that T1 simulates T1. So this is a, let's say, a painstaking thing to check, but in the end it's nothing else than composing the encoders and decoders and delay functions in suitable ways to show this. The reflexivity is clear. Second of all, every reasonable construction of a universal TM from, a universal Turing machine from the literature should be compatible with this. Should be compatible with this notion, or with the notion of local universality. And the one that is the hard to prove is that it excludes all pathological examples like that one. So these two are very difficult to check, especially because there's a wide variety of examples. So just a remark is this definition works reasonably well if we are interested in universality, but if we are interested in, let's say, weaker flavors of computational power, for instance, can a particular Turing machine do addition, then we would have to restrict clearly the encoders and decoders more, such that their complexity is strictly lower than the thing you want to study. So one particular other choices that might be reasonable is, for instance, to say that the encoders and decoders are some Boolean circuits of some constant depth and potentially unlimited width. Or maybe you would come up with other examples based on the context that you study. So one important remark is that we define this for Turing machines. Yes?
Does the second point just mean that a reasonable universal Turing machine should also be locally?
Yes, yes. Yeah, exactly this. Yeah. So it's almost a sport to show that various types of systems are Turing complete, like the Excel spreadsheets or a game of billiard. And so it would be nice if such constructions, if they're reasonable, are compatible with this and are also locally universal in our sense. So that being said, Turing machines are, let's say, not the only architecture of computation on finite symbols, and the definition of local simulation could be readily extended for other types of systems, as long as in the end we have some configuration space that can be embedded or encoded into sequences over some finite alphabet, and as long as the let's say global map that acts on such configurations is a deterministic function. So one particular example that we will encounter later today is, for instance, a cyclic tag system. So a cyclic tag system, C, is defined by a finite sequence of appendants alpha 0, alpha 1, all the way to some alpha z minus 1, with z being some natural number and each alpha I is just a binary sequence. We can denote the symbols by yes and no, for instance. So this induces the following computational process. So on input x, which will be also just a configuration of or a sequence of yes and no's, we initialize the system like this. So the tape will contain exactly the symbols of the input, and we will put a pointer to the first appendant. And what happens now? How do we update this system? So we delete x0 from the beginning of this configuration, and if x0 was a yes, we append alpha 0 to x, otherwise we do nothing. And then we increase the appendant index from 0 to 1, or in general from I to I plus 1 modulo z. So this is the cyclic. So we will just be cyclically going through the appendants, and based on what is the first symbol, we either skip it or append it, and that's it. In some sense, it feels maybe simpler than a Turing machine. And a good notion for why it is simpler. Okay, let me first show you an example so that it is crystal clear. Maybe I can fit it here. So for instance, the appendant list can just be y, 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 and n. And the starting tape can be y. So we delete this, and since it's a yes, we write y, y, y. And now we change the index to here. So now since this is a y, we do append also this one, and we change the index here. Then we also append, and we change the index here. We also append the next. So what are we appending now? The n, and we change the index here. And now since this is an n, we will not append the y, y, y. So, and we change the index here. is this clear? So yeah, the example turned into a definition. Isn't that sneaky? So just to finish it, so it's proper, we can say that the configuration of C lives in, for instance, this space, where this represents the tape content and this represents the current appendant. And then this computational process again induces the dynamical system, which just acts on this configuration space. And now you can notice that in the definition of local simulation, we did not use any particular property of a Turing machine. We just operated on a space of finite symbol sequences, and we had a deterministic map. So you can just use you can like readily extend the definition to also now talk about what it means for a Turing machine to simulate a cyclic tag system, or what it means for a cyclic tag system to simulate a Turing machine. So this is a claim we will not prove. The proof has about 20 pages, so there's not enough time. So the easy claim is that each cyclic tag can be simulated by a Turing machine. That should not come as a surprise. You can easily imagine that you have the contents of the tape on the Turing machine tape, and you also write this appendant list, and then the Turing machine just always deletes the first symbol, looks what's the next appendant, and either appends it or not. I mean, you can just code this on your computer, so that's... what is interesting is that it also works the other way around. So each, let's say, binary, just for simplicity, meaning that the tape only contains zeros and ones, for instance, can be simulated by each binary Turing machine can be simulated by a cyclic tag. So as a result of this, we have that there exists a locally universal cyclic tag. Because there exists a locally universal Turing machine that only uses these two tape symbols. This will become useful in just a second, but let's finally turn our attention to cellular automata. So the final question is, what does it mean for a cellular automaton to simulate a Turing machine? And here, to come up with a definition that is compatible with all the constructions from the literature is quite a challenge. We will only cover, I will only show you an attempt that is reasonable enough, but definitely does not have that property. But I think it's the most natural attempt. And what is the attempt? We will essentially only define it for cellular automata with a quiescent state. But here's the problem, right? We're now comparing an infinite configurations to these finite configurations of these local computational systems. And it makes sense to only encode them into some finite bounded region of the CA configuration. So how do we determine this region and what is outside of it? So the most natural way is to just require that everything except for this finite region is the quiescent state and does not change. And essentially, if you view a CA as acting on its subspace, where only a finite region is non-quiescent and everything else is quiescent, you can kind of canonically encode this region into such a configuration space over finite sequences, which will allow us to compare the two. It will turn out that this is too restrictive, and I will show you an example of that. So let A be some d-dimensional CA with some fixed quiescent state Q. So I already did define this, but essentially we can now define the configuration space of A to be this, which is nothing else than all the configurations such that C differs from Q only on finitely many positions. And it is quite clear that if we restrict F to this subspace, it will be a self-map of this. And now in D equals 1, it is extremely straightforward that we can identify this with sequences over S with the clean star. We can, let's say, identify and in higher dimensions, okay, in D, we use some canonical encoding of this region into a star, which we can now call the configuration space of A. And now we have a map F from the configuration space of A, or maybe let's call it local configuration space to like distinguish it from all of the configurations. And now we can readily compare it to Turing machines in the exact same way as we did. So a canonical example of this, which is very trivial, is what happens when we actually have the freedom to construct a cellular automaton to make it locally universal. So an example is the talking heads example. Next week we will see non-talking heads, but now we have talking heads. So for, let's say, universal Turing machine U, we define HU where S will be essentially something like sigma prime times Q together with some some special state which is not included anywhere else. And so where, let's say, okay, and for, so let's say, and the state SQ denotes the tape symbol S and the presence of a head in this particular location and the state S then denotes the tape symbol S and the absence of a head. So, since we're running out of time, I will not write down the exact way we would define the local rule, but essentially what we are doing now is that, actually this is just a one dimension, we can define it in one dimension, in the sense that now really the initial configuration which represents the Turing machine configuration is exactly this, and now the local rule just encodes exactly the update function delta. So it's gonna, essentially the local rule will keep all of the tape symbols static except for the one where the head is, which will update the state, and the states around it, which based on the head's movement will now change into the corresponding state. And this only essentially specifies partially the local rule, and we don't need to even care how we define it outside of the region. For instance, if two heads interact and they are, so the configuration space of the CA will also include configurations where there's multiple heads on the tape, and we can define their interactions however we want. So the quiescent state here is just the blank symbol and this. So we define the local rule of HU to encode delta. I'm sure you can all fill in the details. So naturally, we can now talk about the local universality of cellular automata. Essentially, a cellular automaton is locally universal if it can locally simulate any Turing machine, or equivalently if it can locally simulate a locally universal Turing machine. So. So some more reasonable properties that should now be satisfied by local simulation is that it is compatible with global simulation. So so part 2. So let's say if B, which is a CA, globally simulates A, which is a CA, and A locally simulates a Turing machine T, then it would be a pretty natural requirement to have that B also locally simulates T. And that is pretty straightforward to verify, and it immediately leads to the statement that, if B is globally universal, then it is locally universal. I think let's end here for now, and I will use the first 10 minutes of the exercises to show you a demo of what happens if you find a cellular automaton in nature, or you open the door and you see a present where someone gifted you a cellular automaton, and you would like to understand whether it is locally universal. What are the strategies to have? And in some sense, I will show you a very high-level overview of some of the most elaborate constructions of, or let's say, proofs that show that a certain very, very compact one-dimensional cellular automaton is Turing complete, and that, or locally universal, and that we will, in order for that particular example to be accepted by our definition, we have to generalize it. But I will not give you a formal definition of that generalization. So let's take a break and start at 15. So what you see here is the rule table of an elementary cellular automaton 110. Essentially, the description of this CA is just 8 bits of information. Yet it was proved at the beginning of the 2000s that by Matthew Cook in a very elaborate manner that this CA is in some sense locally universal. So it almost sounds like a mystery. How can 8 bits of information encode universal computation? And it becomes less of a mystery exactly when you explicit the encoders and decoders that are underlying this process. Because the process is not, as I say, is quite elaborate, and it starts by reducing an arbitrary Turing machine to a binary Turing machine, then reducing that binary Turing machine to a clockwise Turing machine, which is something you will do at the exercises. Then it is to reduce the clockwise Turing machine to a cyclic tag system. And lastly, you show that Rule 110 can simulate a particular class of cyclic tag systems, which also includes a locally universal cyclic tag system. So what is a pretty impressive result is that these encoders and decoders and delay functions that are underlying these are, let's say, all just polynomial. So in some sense, this resulting simulation is still feasible in a theoretical sense. But composing this many polynomials still means that if you wanted to compute something in practice with Rule 110, you would have to be extremely patient. So essentially, these previous reductions are standard in the literature, even though some of them are very elaborate, for instance, this one. So in the exercises you will focus on this one. And now we will focus on this one. So we already know what the cyclic tag system is. So what would you do if you were gifted a CA? So a first initial observation that is nice to make is that whether you can see some gliders. It's not that it is a necessary condition for universality, but usually if there are some gliders that move through some constant medium and they interact with each other in ways that are rich enough, you might hope to encode in these glider interactions some information processing, like some basic logic gates. But that's extremely hard in one dimensions, where information can only flow in so many directions. So that's why the cyclic tag system is, let's say, a more suitable architecture than a general Turing machine, if you want to compare the two systems. So this is a scheme from Cook's paper which illustrates this. What you see here is a cyclic tag system which has two appendants, one YYY and the second one N. Coincidentally is the one I showed you as an example, with the initial tape symbol being Y. And this is essentially, let's say, a very high-level overview of the space-time diagram of Rule 110 and how it encodes that information. So let's go back to the space-time diagram. One thing we can notice is already that the gliders are not gliding against a quiescent background. This background is sometimes called the ether, and it is a periodic thing in itself. So already this would not fit our definition where the CA has to have a quiescent state and everything is encoded within a finite region surrounded by this state. But that would still be, let's say, salvageable in a straightforward way. For instance, just packing the Rule 110 and only looking at every... So let's say this ether has like a spatial period of 14 and a temporal period of 7. So all you would have to do is, let's say, pack the cellular automaton into supercells of size 14 and look at every 7th iteration or every 14th iteration, and this ether would look like a quiescent state. But the situation is even worse in the sense that we unravel more than just a periodic background on the space-time diagram. So there's two types of periodic structure. So there is the static, let's say, finite region, which encodes the information about the tape. And then to the left, there is like a periodic repetition of certain type of glider, which is called the ossifier. And to the right, we actually periodically unravel this appendant all over again. So essentially, this is an infinite configuration which consists of glider which represents YYY. Those are these three lines. Then there are some leader gliders, which also are something. And this is then followed by a glider representing N, and that is again followed by a glider representing YYY, and so on indefinitely. And what happens is that at every update, one of these appendants gets destroyed. That's why you have to supply infinitely many of them if you want the simulation to work for arbitrarily many time steps, and it works like this. So essentially, every kind of sequence of gliders which represents a certain appendant has a certain leader that kind of travels in front of it. And this leader always reacts with a tape symbol. So here the tape symbols are actually written from right to left. So now the first tape symbol is this Y. And it essentially activates the leader, which now travels back. And if this symbol was a no, as you can see here, the active leader erases the whole appendant so that it does not react in any way with anything else. And it essentially, we have both accomplished deleting this symbol and not appending anything, so that's great. If the symbol is a yes, then essentially this leader activates the following appendant, which is then able to pass through all the subsequent symbols that might be on the tape until eventually they hit the ossifiers that come from the other direction. And this collision of the two will essentially transform this traveling glider into a static tape symbol. So it is very elaborate to like define the encoders and decoders. A particularly nice way introduced by Cook to define the encoder is through these puzzle pieces. So here you, for instance, see that every Y symbol will be represented by these 4 static gliders that just glide down in time. And essentially every N is represented by the same gliders, just with different distances between them. And these have certain periodicities when it comes to how they exist with respect to their neighbors compared to the ether. So they can be placed into the ether with in different kind of temporal and spatial positions. So that's why we have these puzzles here to ensure that if you glue together 2 blocks, the relative phases will always match such that this simulation works. And this is quite complicated. But essentially you can build the initial tape content by puzzling together these pieces representing Y and N. Then you will always puzzle to the right a leader. And after the leader, you will kind of puzzle together some of these pieces which will encode each of the appendants. And to the left, you will puzzle this with a big enough chunk of static background, which is the ether, and then with these ossifier blocks. So let's not go into too much detail. But essentially, one problem you can see is that if we did not append once in a while something, what would happen is these ossifiers that travel will eventually hit a tape symbol. And that will destroy this whole construction. So this kind of shows that the rule 110 is not able to simulate every particular cyclic text system, but only some admissible cyclic text systems, which have the following property. Like every time you go through the appendant list, you have a guarantee that you will append at least one non-empty appendant to the tape, such that the ossifiers will essentially never hit the tape symbols if you place them far enough from each other. So luckily, one can show that there is a locally universal cyclic text system which has this property. The second property is that actually each appendant's length, if it's non-empty, has to be a multiple of 6, such that the relative phases with respect to the ether match. You will be able to show in the exercises that every cyclic text system can be simulated by a cyclic text system which has these appendants to be a multiple of 6. But, okay, maybe this is a good time to show you the implementation of this, which I did, and I'm still surprised that it works. So this is in PyCA, which is the other, let's say, simulation tool that was hopefully showed to you by Asan at the beginning. So rule 110, universality. So I think here the initial tape is YYN, and we only have one appendant of length 6, which is YNN, YNN. And if we run this, so here you see the 3 tape symbols. Orange means no and black means yes. So what is happening is here is the first appendant arriving. It interacts with this yes. It is being activated to be able to pass through the remaining tape symbols. And once it passes through the remaining tape symbols, it hits these ossifiers to create the new appendant, which should be YNN, YNN. And there's already, in the meantime, there's another appendant hitting the next tape symbol, which is also being activated and just passes through. Obviously, this runs very slow because I'm just showing you a finite portion of a very big configuration. Yeah, so, okay, we missed that, but okay, here's another one that's passing through. But so the next symbol will be an N, for instance. And when the appendant hits an N, you can see how it's being erased. But what is fun, actually, is that even every collision between an appendant and a tape symbol creates some junk. This junk is seen, for instance, here. And it will forever be present in the configuration. It's not going to interfere with anything. It's just going to pass through all the tape symbols on the tape, which are now scattered in space, and they're very far apart, so we have to travel through the configuration to see them all. So now you can see, for instance, the junk just harmlessly passing through the tape symbol, which actually makes the simulation reversible, in the sense that if you look at the configuration of rule 110, from all the junks you see, you're able to trace back what were the collisions. So in some sense, rule 110 simulates the cyclic tech in some reversible manner, even though it's not a reversible CA itself. So that for the demonstration. I hope it's at least believable that it works, because there's so many layers of details one has to make sure that they work, that it's really still a surprise. But just to give you an intuition for how we could make the definition of local simulation more general to account for this case, well, first of all, we should not only allow for quiescent backgrounds, but for some admissible backgrounds. So for instance, they could be some simple patterns, like this ones, or even like some convex regions, let's say finitely many convex regions, where each has different periodicity of some pattern, which is the case for rule 110. Second of all, there is now this junk that keeps on growing and extending this region, which does not just contain the background, which is something like that case, which is not very desirable. So we actually only limit the decoder to have a finite bounded window where it can look at the relevant information, such that it does not try to decode junk, which is just growing over time. So this is kind of now allowed by these two shift operators, which always shift the relevant information back around the origin, and the decoder can just kind of access this information about the origin to decode in some computationally bounded ways. So once you extend the definition of a CA simulating a Turing machine to this more general sense, it is compatible with rule 110, and it also shows one, so I already discussed this theorem. There is one more interesting result, which is that for every dimension there exists a reversible d-dimensional cellular automaton that is locally universal. So we discussed that reversible cellular automata cannot be globally universal, but with this broad enough definition of local simulation, we have that reversible cellular automata can be locally universal. So maybe just like a quick picture of what is the intuition behind that is that in some sense, basic logic gates are inherently irreversible. Like if you have an OR gate, there's two input bits and just a single output bit. So some of the information got processed, but also some of it got lost. So if you want to have reversible logic gates, for instance, if you had any course on quantum computing, the classic trick is to actually introduce auxiliary outputs which now collect garbage. I don't know, like it could, for instance, be A XOR B, and like from these two outputs you can then reverse the inputs, which now is the intuition behind what's going on. If you have local simulation, you can produce, as you iterate, more and more junk, and this junk can kind of propagate through the space. But if you have, and if your decoder only focuses on the relevant information, you can show that you have reversible cellular automata simulating Turing machines, like universal Turing machines. But if you have global simulation, you don't have this unbounded space where you can store this garbage, because you only have, let's say, a constant blow up in time, which is what kind of resulted in our, in the result that you cannot have globally universal reversible computation. So in some sense, reversible systems can compute, but there is a price to pay for it, which is this bookkeeping of the extra bits that will allow you to reverse the inherently irreversible logic gates. And so, from what we have seen, global universality is a strictly stronger property than local universality, because the class of universal reversible cellular automata sits in between. So here you see an example of like a cellular automaton representing a billiard ball that keep bouncing around, and in the way they bounce, you can kind of, from the way they bounce, you can show that it is locally universal. And now the interesting question is what other systems can lie in between these two, for instance. And as you will show as you will see on the next lecture, which is actually not next week because it's a holiday, but the week after that, probably by my collaborator Jordan Kotler, there is another interesting class that sits in between the two, which is a class of cellular automata that can self-replicate, or that satisfy some necessary conditions for self-replication. And that's it. Good luck with the exercises. And yeah, if you have any questions, I'm here.